So, the final thing that we need to discuss in chapter 3 is what happens when we apply a small perturbation in one of our aerodynamic forces or in pitching moment. How does that change the coefficients that we've just derived in the previous sections? So, oh, and by the way, the eagle-eyed among you will have noticed I can't spell modelling consistently, and that's because in British English it has 2 L's and in American it has 1, so forgive me on that. So if we think about what variables are affecting, let's start with our drag force. So what variables affect the drag force? Well, angle of attack affects our drag force, the forward speed of our aircraft affects the drag force, pitch rate will affect our drag force. If we change the angle of our elevator or of the horizontal tail will affect drag, and also the rate of change of angle of attack will affect drag too. And all of these variables also will affect our lift force and also our pitching moment. So what we do is we assume that a small perturbation in lift or drag force is a function of small perturbations of all of these variables here. So that's what I've written down in this system down in here. So a small perturbation in the drag force is a function of small perturbations in the forward velocity, in angle of attack, in the rate of change of angle of attack, in the pitch rate. So remember, this Q here is not dynamic pressure, it is a small perturbation in pitch rate, in changing elevator angle, and in inclination angle of the horizontal tail, and so on and so forth for the lift, a small perturbation in the lift force and a small perturbation in the pitch moment, little m. So as we've done in all of the previous sections, we can go ahead and apply a Taylor series expansion to each of those about the steady state condition, which we're now going to use the terminology SS, so this derivative evaluated at the steady state condition and then multiplied by all of the small perturbations to get this system down here. And then the next step there is to non-dimensionalize these systems here, because ultimately we want to find what's happening to coefficients, right, which are non-dimensional. Some of these terms are dimensional, right? So obviously small perturbation in the forward speed has dimensions. The angle of attack and the angles of the elevator and the horizontal tail are going to be in radians, so they're already non-dimensionless. So we will have to non-dimensionalize U, alpha dot, and Q. So that's what we do over here. The textbook uses these transformations up here. We non-dimensionalize U by dividing it through by something that's got the same units as U, namely the VP1 vector, and so on for the other variables. And that allows us to write a non-dimensional version of this thing that we just had down here. So how do we get from all of this stuff, which is all in terms of derivatives, how do we get from something that looks like that into something that's in terms of the coefficients that we've just seen? Well, this is spared in the textbook. All of this is derived in this Roskam book from 1995, but basically we write these derivatives in terms of coefficients to get this stuff. And you'll see that in the small perturbation in the drag equation, you have mostly drag coefficients. There are a couple of lift coefficients that affect that as well. And then in the small perturbation in lift coefficient, in lift force, obviously you'll see mostly lift coefficients. Again, there are a couple of drag coefficients that contribute to that also, but it's mostly lift coefficients. And then in the small perturbation in moment coefficient, you'll see there's mostly moment coefficients in here, look. So now we need to talk about what each of these coefficients is and how we can either model them or approximate them, right? So in these three equations here, there's actually 12 of these coefficients, right, which we're going to call the dynamic derivatives. apart from all of the ones associated with the steady state condition. They're things that we've already seen before, right? So what I've got on the next page here is a list of these 12 coefficients, and now we're going to talk about what each of them means and how we model or approximate them. So all of the ones with subscript 1s we've seen before, they're the drag and lift and pitch moment coefficients associated with the trim condition. And obviously we, by definition, we have net moments to be 0 when we're in the trim condition, so we can set CM1 to be 0 by definition. And then what we have after that is 9 what we call dynamic derivatives. So CDU, CLU and CMU are the drag, lift and pitch moment coefficients due to small changes in the forward velocity, u. And a couple of these have special names, namely CDU, which is called the speed damping derivative, and that can be approximated as 0 for subsonic speeds, right? CMU is given the name the Mach-Tuck derivative, and that also can be approximated as 0 for subsonic speeds. But what happens as the aircraft goes subsonic is the aerodynamic center moves rearwards, like we saw with aerofoils, right? And that tends to give us a nose down pitching moment. So for the subsonic applications that we're considering in this course, we're going to assume that these two are both 0. Next we have the drag, lift and pitch moment coefficients due to small changes or small perturbations in the rate of change of angle of attack, alpha dot. And again, so no special names for these ones, but CD alpha dot, again we can assume is 0 for subsonic speeds. And generally in these terms we only consider the contribution of the horizontal tail, because we assume that the contribution from the wing and body is negligible, because basically these coefficients describe how, as the angle of attack is changing, what happens is the downwash due to the change in angle of attack hasn't yet reached the horizontal tail, and so basically the angle of attack on the horizontal tail is greater than we would normally predict in the steady state condition, because as the angle of attack is changing, so this is the change in angle of attack, right, it hasn't actually reached the horizontal tail yet. So we have a discrepancy there that we need to compensate for. And finally then, the drag, lift and pitch moment coefficients due to small perturbations in pitch rate, little q, right? So this time we assume that CDQ is 0 for subsonic speeds. Obviously I'm missing a 0 in here. Okay. And in this case, so we only considered the contribution of the horizontal tail in these coefficients here. Down here we consider the contribution of both the wing and horizontal tail, but generally don't consider the contribution of the body. And also we assume that the contribution of the wing is small in comparison to the contribution of the tail, because the effect of the tail is much larger because we have a much larger moment arm associated with the force acting on it. So that's it.